Okay, good morning everyone. I hope you are doing well. Kalau ada yang tak sihat tu, please stay at home. Jangan keluar mana-mana and take care of yourself, eat your medicine and all that. Okay, so today kita akan continue with chapter 11. Previous class, we finished chapter 10. So now we are doing chapter 11, which is on geometrical optics. So for this chapter, we will cover reflection and refraction, dispersion, and also spherical mirrors and also thin lenses. So reflection and refraction, I believe you have learned this in high school, but it's okay, kita akan belajar balik. And then dispersion, I think is new. Spherical mirrors pun dah pernah belajar, but okay, kita akan belajar balik. And then thin lenses, I think it's new for you guys. So let's start. So for this chapter, we are going to try to solve problems on reflection and refraction. This is your learning outcome. Explain what is dispersion and if there is any application related to it. You have to know how to draw the ray diagram for spherical mirrors. This is like straightforward. Solve problems on spherical mirrors. You know that you have like equations related to mirrors and you will use that to solve the problems. Draw ray diagrams for thin lenses as well. And then solve problems on lenses. Okay. So brief introduction on light waves, light as waves. So when light propagates, it also propagates like sound in a sense that it also travels through a surface. Remember, I told you sound propagates in the form of spheres. And at that point, at that same radius, you know that they have like the same property, or in the sound case, we know that at the same radius, they would have the same intensity, right? So this will be intensity. If I'm staying over here and Wasila is over here, so me and Wasila will hear the same sound ataupun the same intensity. So the same case for light, tapi it's not intensity. Light also propagates outwards, and we call that the light that has the same radius. I wouldn't say it's radius, like the light that travels through a surface is called ray, and this guy over here, benda lah yang kita panggil sphere hari tu, waktu kita belajar sound, is called a wave front. It's called a wave front. So wave front is a surface, same like before, surface passing through points of a wave that have the same phase and amplitude. Now remember, for sound, it was the same intensity. For light, if you have like the same radius, that's not the official term here. If you have like the same distance, you would have the same phase and amplitude, and that ray will travel through the wave front. Sorry, it is called the wave front. And ray is a line corresponding to the direction of the wave motion. So in this case, it is traveling outwards. So we would call this as rays. Okay, and these guys are the wave fronts. So that's just a term you have to be familiar with. So far away from the source, the wave fronts are nearly parallel planes. So as we propagate, we can see that dia nampak macam almost like a straight line, tapi sebenarnya dia curve. But when the curve is like too big and we only take a section of this curve, we can see like it's almost like a straight line. Okay, so it's almost, the rays are almost perpendicular lah to the wave fronts. So from far away from the source and taking like a small section of the wave fronts are nearly parallel planes. Almost lah, sebenarnya it's not really parallel, but it's almost like parallel. So a small segment of the wavefront is approximately a plane wave. The rays are parallel lines that are perpendicular to the wavefront. Perpendicular. So they are parallel to each other, but they are perpendicular to the wavefront. I'm so sorry for my voice. Okay, so a ray of light is an imaginary line drawn along the direction of travel of the light beams. We saw this. So this is like our imaginary lines indicating the direction of light. The ray approximation is used to represent the beams of light, and light travels in a straight line path in a homogeneous medium until it encounters a boundary. And we have seen that if our wave hits a boundary, it will either reflect ataupun it will either transmit. Sorry, this is like terrible drawing. So it can go through two things, either it will transmit or reflect, or it can be both reflected and transmitted. Last time our diagram was like this. This is our wave, and hitting a boundary, it either reflects back onto itself, or it is transmitted and becomes smaller. That was what we learned for waves in chapter 9. So here kita akan draw our light not as sine waves, but we will draw it as arrows, so it's simpler because we will deal with ray diagrams later. So untuk untuk waves in general, we drew it as sine waves, but for light kita akan go for arrows to indicate its direction. Last time our direction kita indicate macam ni je. Okay, it's the same thing, but kita nak senangkan hidup kita guna arrow je. Okay. So reflection and refraction of light. Light travels in a straight line path in a homogeneous medium until it encounters a boundary between two different media. Media is the plural form of medium. So you have one medium over here, we call it medium 1, and we have another one over here, we'll call it as medium 2. So this is our incident light. Okay, it's traveling this way. Okay, kalau tengok kat sini dia lukis as sine wave as well because it is sine wave as well. Because it is a wave. So kita travel macam ni, and this is the boundary ataupun sempadan, and it will be reflected or refracted or both. In this case, it is both. So it is reflected this way, and also it is refracted. So previously we called this refraction as transmission. It is the same thing, but here we call it as refraction. Okay, so we have incident ray and we have reflected ray and we also have refracted ray. So here is your boundary between air and glass, which means that they both have different refractive index ataupun they have different properties. Let's call it different properties first. So air has different properties than glass. Why does it have a different property? Because when a wave ataupun when light travels through air versus traveling in glass, the speed is different. Okay, the speed is not the same. Remember, if our wave travels through different mediums, the speed changes, the wavelength changes, but the frequency does not change. So this is the case here. Here we have air and glass. These are two different mediums. The speed in air is not the same as the speed in glass. Okay, so when they have different speeds, we say that they have different index of refraction. This is a new term. Index of refraction, I will write this as letter N. Okay. So air, I would call it as N1. It has velocity 1. The air has a velocity of V1. Sorry, the light has a velocity of V1 in air, and the light has a velocity of V2 in glass. Did I say air or light? The light has a velocity of V2 in glass, and we call this medium to have index of refraction N2. We're just saying that N2 and N1 are not the same. They have different properties and they have different speeds. When they have different speeds or when they have different index of refraction, you would have the light travels at different speed. When it travels at different speed, dia akan either move towards the normal or move away from the normal. Now, what is the normal? The normal is this guy over here. So it is always going to be perpendicular to your boundary, always. Your normal, I'm going to repeat myself here, your normal is always going to be 90 degrees with respect to your boundary. So if you have an incident ray, your angle theta is with respect to the normal. So incident ray with respect to the normal, this is your theta 1. And then your refracted ray with respect to the normal, your normal is here, right? So with respect to the normal, this is your refracted angle. This is your incident angle. This is your refracted angle. And same case for reflected. This is your reflected ray with respect to the normal. This is your reflected ray. Reflected ray, okay. So here, this is like a real case scenario. Here we have an incident ray. Let me use red. This is called the incident. We are shining a laser source over here. Okay, that's a laser, okay? So we are shining a light, laser light, and this laser light goes through a boundary between air and this glass, this block of glass. So we know that the speed of light will change when it enters a different medium. So with respect to the normal, where is our normal? This is our normal. It's not labeled here, but we have to know that the normal is always going to be 90 degrees with respect to the boundary. So this is your normal. And what is your angle of incident? It is over here. And what is your angle of refraction? It is over here. And your angle of reflected, your angle of reflection is, excuse me, is over here. Okay. So it's always with respect to the normal. Jangan label kat sini eh. I know you're tempted to write the angle over here, but that is wrong. You always have to refer to the normal. Selalu satu kesalahan yang selalu orang buat. Okay, so we have like a bunch other here. Excuse me. Okay, so this is your reflected ray, right? So now, for this case, it now becomes your incident. Okay, your incident. Sebab dia macam kita anggap ada dua senario lah kat sini. We have the first scenario and also the second scenario. The first scenario, we had like a laser in air and it goes through a boundary of glass, right? And then our second scenario would be from glass and inside the glass, and then from glass to the air. So let's talk about the glass to air first. So from the glass to the air, this is our normal. Okay, always 90 degrees to the boundary, and your angle of refraction is over here. This is your angle of incident ataupun I, R. This is theta I, and this is going to be theta R. Now, after this is incident and then it is refracted. There's no reflected light over here, but over here we have the reflected light. So this is not the normal reflection. This is called total internal reflection. Kita akan belajar nanti. So what happens is you have this incident ray of light, right? This is theta I. Susahnya nak tulis. Susahnya nak lukis. Tulis. Okay, this is your normal. Okay, this is your incident light, theta I. You have something that is reflected back into your medium. You have something that is reflected back into your medium. And this is glass, right? And this is air. So dia kena achieve a certain angle untuk achieve total internal reflection. Nanti kita akan cakap pasal ni. So I'm just giving you like an overview what we're going to deal with today. So again, I'm going to repeat myself here. We have incident ray. And incident ray is, the angle is with respect to the normal. Normal is always 90 degrees with respect to the boundary. And this is the reflected ray. Now, one thing about incident and reflected angle is that they are equal. Theta 1 is equal to theta 1 prime. Ataupun you can just call them both theta 1 because they are basically the same thing. So incident ray will always have an angle that is similar to the reflected ray. That's just how it works. And then now we're talking about refraction of light. As light travels from one medium to another, the wavefronts do not pile up, nor are they created or destroyed. So its frequency must stay the same. But both the wave speed and wavelength do change. Remember, I told you our wave is, the equation is V equals to lambda F. everything changes except frequency when it travels from one medium to another. So here we know that when we have different speeds, we will have different index of refraction. Index of refraction, nama pun refraction. Index of refraction is labeled as N. So here we have N1 and N2. N1 is equal to C over V1, where C is the speed of light in vacuum. And this is a constant. It will be given to you in the exam or in your quiz, because chapter 11 and 12 is in your quiz. So C is equal to 3 times 10 to the 8 meter per second. This is basically the speed of light in vacuum. This is like the fastest. So to find the index of refraction, it is equal to N is equal to C over V1. So V1 is the speed of light in your medium. So it is basically a ratio of speed of light in vacuum over the speed of light in the medium itself. Okay. So here we have N2, it is also C over V2. Excuse me. I think I need something to... So when light passes from one, saya makan gula-gula. So when light passes from one medium to another, I sound different. It is refracted because the speed of light is different in two media. We already talked about this. Light may refract into a material where its speed is lower. Light may refract into a material where its speed is lower. So typically kita akan cakap pasal this is air and this is glass, and we know that the speed of light is the fastest in vacuum. So this gives you an idea that when it travels through something that is higher in density, such as glass, it will travel slower. So speed of light is the fastest in vacuum, and then in air, and then in whatever medium lah, contohnya glass. So urutan dia macam ni lah. So when your light travels through a medium that has a higher index of refraction, it will travel slower. When it travels slower, this ray will be reflected towards the normal. Refracted. It will be refracted towards the normal. Sebab dia jadi slow. Bila jadi slow, dia macam berkuranglah angle tu. Reflected towards the normal. So you can guess already what happens when it travels from a medium of high density to a medium of lower density, ataupun N1 is greater than N2. Contohnya kita travel from glass to air. I think you can guess already. So this is my normal. This is my ray of light. This is my incident angle, right? Theta 1. So if I told you just now, if it becomes slower, if the speed of light is slower, it will go towards the normal. If it becomes faster, it will travel away from the normal. So kat sini angle dia jadi besar. So it is refracted. Sorry. It is refracted away. Dia menjauh dari normal, refracted away from the normal. We have two instances here. I'm going to repeat myself. When you are traveling from air to glass, ataupun N1 is less than N2. This is air and this is glass. Glass lagi tumpat. Glass has a higher index of refraction. With that said, we know that the speed is also slower in glass. So when the speed is slower in glass, it will be refracted towards the normal. And then when we are traveling from a medium of high density to low density, or with a high index of refraction to a medium of low index of refraction, the light will be refracted away from the normal. This is something that you need to remember, okay? Okay, so again, we talked about n. N is speed of light over your speed of light over the speed in the medium itself. So if the speed is called v1, then your n is called n1 lah. It has to match. So if you're talking about medium number 2 and the speed is v2, so please label your n accordingly, n2. Okay, so they correspond to each other. So this is going to be n1 and this is going to be n2. Okay, I have a question here. Ikri asked me, so Dr. Sun ray also refracted when it came from outer space into atmosphere. Betul, it is refracted, but actually betul, it refracts because it enters from vacuum to a high density. Our air is high in density, right? This is how we are breathing. But with that said, I hope you don't confuse this with the color blue of the sky is not due to refraction, but it is due to scattering. Okay, let me write that somewhere. That's a really good question. So Ikri is asking, so this is our Earth, and we know that our Earth gets light from sun, right? Excuse me. So assuming this is my sun lah. Okay. Okay, this is sun. So it has rays of light, travels everywhere. And then we have our atmosphere over here. Okay. So our atmosphere is dense. So again, when a wave is traveling from something that is low in density to a higher density, ataupun they have different index of refraction, the speed will be different. When the speed will be different, they will be refracted. So I don't know which way it refracts, maybe everywhere. Okay. But this does not give you the color in the sky. Refraction is not the cause of your blue color in the sky. The blue color in the sky. Oh yeah. I think that was a video from this class. Oh no, it was a video from K7. So the blue sky, the blue light in the sky that we see, okay, is actually due to scattering. Where do I write this? But the blue color that we see in the sky is due to scattering. Sama juga macam sunset and sunrise, we see like orange and yellow color in the sky. It is actually due to scattering. For the blue color, it's called Rayleigh scattering. I'm just introducing this to you guys. Don't have to memorize it. Don't panic. It's a term in physics. I'm just trying to tell you. So Rayleigh scattering gives us the blue color in the sky, and this is also the same case for sunrise and sunset when we see the red and yellow color. But betul, Ikri tanya tu betul. The sun does refract. The light from the sun does refract when it enters the atmosphere, but it does not give us the color. The color is caused by scattering. Okay. Okay, for a vacuum, I told you light travels the fastest in vacuum, and it would have the index of refraction of 1 for vacuum. So again, physics likes to simplify things. So in this case, we are also assuming air has the same index of refraction as vacuum. Even though we know that in vacuum, they travel lagi faster, tapi they approximately the same lah. So they said, okay, let's just call N in air as 1, the same as vacuum to make our life easy and to make approximation simpler. But for other mediums such as glass, water, the index of refraction must be greater than 1 because the speed of light is slower. Again, N is equal to C over V. When your V is slower, it means that your N has to increase. This is why our N is greater than 1 when we travel from air to a medium of higher density. Okay. Okay, moving on. Excuse me. So these are indices of refraction. Indices is plural for index. Indices of refraction for various substances measured with light of vacuum wavelength 589. So they checked and they found out that the index of refraction for diamond is 2.41, 2.419, and in air, such as carbon dioxide, it is close to 1. This is why they approximate it to just equal to 1. And then for liquids, such as water, it is 1.233, a little bit higher than air, but not too high. Diamond is like very dense. Okay, so now we're going to talk about Snell's law of refraction. So remember I told you we have the incident angle and also the refracted angle. We also have a reflected angle over here. How do I distinguish between refraction and reflection? I'm just going to write it reflected. So we have incident angle, reflected angle, and also refracted angle. Reflected angle must be equal to incident angle. Refracted angle can either be greater than incident angle, or it can be less. Okay, so when it is greater, you know that it is traveling away. If it is moving away from the normal ataupun moving away from the normal, means that it has high speed or low index of refraction. When it is traveling towards the normal, you have a smaller refraction, you have a smaller refracted angle than the incident, and you know that this is because you are traveling into index of refraction that is high and your velocity is slower. Kalau slow, dia bergerak, dia mengurangkan angle. Ya Allah, susah nak cakap. Okay, so this is what we learned earlier. Okay, parking jap kat sini. Okay, so now Snell's law tells us that the ratio of the sine of incident angle to the sine of refracted angle is always constant. It is always constant. So when sine theta 1 over sine theta 2 is constant, of course, we have an equation later on. So the bending of light is due to the change in speed of light in two media. Therefore, we can equate it like this. Sine theta 1 is equal to V1. Sine theta 2 is equal to, sine theta 1 over sine theta 2 is equal to V1 over V2. Abaikan dulu yang ni. So kita rearrange this. Saya kena abaikan V. Kita tahu when we have different V's, we will have different N's, right? So here, Snell's law tells us N1 sine theta 1 is equal to N2 sine theta 2. I think this is like basic equation that you already know. Because of the speed of light is different in these two mediums. So theta 1 is the angle of incident and theta 2 is the angle of refraction. So this will be your index of refraction in medium 1. This is your incident light. Dia kena match incident light. And N2 will refer to your refracted light. Okay. So now I'm introducing to you guys ratio N2 over N1, V1 over V2, and also equal to lambda 1 over lambda 2. Tadi kita cakap pasal N1 sin 1, N1 sin theta 1 equals to N2 sin theta 2 kan? Okay, sekejap. I need to derive this. Bear with me, I have to, because nanti ada orang katanya. Okay, sekejap. Tu fikirlah. And of course, it is important for you to understand juga lah. You don't have to memorize, you don't have to know how to derive it, but it's important for you to, have an idea how it is derived. Okay, so frequency stays the same as a wave travels from one medium to the other. We know this. everything else changes except the frequency. I want to use a different color. Everything else changes except frequency. So frequency is like the winner here. So with that said, we know that V over lambda is equal to F. If F does not change when it travels from medium 1 to medium 2, okay, so F does not change, but V1 is not going to be the same as V2, and maybe lambda pun tak sama. But we're going to talk about V dulu. So with that said, I have an equation, V1 over lambda 1 is equal to F for this side, and V2 over lambda 2 is equal to F on this side. So if I can equate these two guys together because they have the same frequency, right? So I can write it like this, V1 over lambda 1 equals to V2 over lambda 2. So I have like this ratio. Wait, I haven't. Gonna rearrange dulu. So V1, I'm rearranging this to have V's on one side and lambdas on the other. So V1 over V2, I'm bringing this guy down here and this guy over here. So I have lambda 1 over lambda 2. So now I have this ratio. V1 over V2 is equal to lambda 1 over lambda 2. This is our first ratio. Moving on. How do I get the N1 and 2? Okay. So remember that we talked about index of refraction. Where I need space. Or just duplicate this. Okay. I also told you guys about the index of refraction punya equation. Okay, so this is N is equal to C over V. So if this guy has V1 and this guy has V2, I know that I would have N1 and also N2. Okay, so N1 is equal to C over V1 and N2 is equal to C over V2. Same case over here. We can equate these two C's together because C does not change anywhere. C is a constant. So if I were to rewrite this, N1 V1 equals to C, N2 V2 is equal to C, I can equate these two guys together. So now it becomes N1 V1 equals to N2 V2, and I rearrange this to have V's on one side and N's on the other. So this becomes N2, this becomes V1 over V2, N2 over N1. So now I have this guy over here. So because N2 is equal to N1, sorry, N2 over N1 is equal to V1 over V2. Okay, we saw it over here. And we saw earlier that V1 over V2 is equal to lambda 1 over lambda 2. I can actually say that N1 is also equal to lambda 1 over lambda 2 punya ratio. So this is an equation that you need to remember, ataupun this is the ratio that you need to remember and apply. So boleh, it works either way. So V1 dengan lambda, N2 N dengan lambda, N dengan V, dua-dua boleh. So one thing to remember here is that you can see that this is 1, but this is 2. So V dengan lambda akan have the same denominator, subscript, and index of refraction is the odd one here. So we have, kalau saya cakap kat sini, this is X, this also needs to be X. This is Y, this also needs to be Y. If this is X and this is Y, this needs to be Y and this needs to be X. So kena ingat index of refraction je yang odd one. Okay. Okay, so let's go on to example 11.1. So far, do you have any questions?
No.
Tadi, okay, I'm going to continue. If you do, please interrupt me. Okay, so a ray of light strikes a thick sheet of glass. Okay, so a ray of light strikes a thick sheet of glass. Let me draw this glass. Walaupun buruk. So it's thick. Okay. So let's draw our ray, our normal, sorry. Our normal. Normal is always 90 degrees with respect to the boundary. And then our ray of light strikes this thick sheet of glass at an angle of 25 degrees with the normal. 25 degrees. Okay, so find the angle of refracted ray within the glass with respect to the normal. So from assumption lah, we know that this is air and this is glass. So what happens to the ray of light when it enters glass? Is it going to move away or is it going to move towards the normal?
Towards normal.
Towards the normal because it is moving slower. So I'm going to draw it like this. And we want to know what is the angle. So the angle is not here. This is wrong. The angle is with respect to the normal over here, theta. We draw that in a different color. So this is color blue, theta. Okay, so we are finding what is theta over here. So using my Snell's law, n1 sine 1, sine theta 1 equals to n2 sine theta 2. Snell's law is specifically for refraction of light. So n1 is referring to the medium where the incident light is. So air, we know that air is going to have 1. Kita tahu tadi from approximation, air is lebih kurang dengan vacuum. So we're just going to say it's 1. So sine theta 1 is 25. And then n2 glass is 1.5. And then we are trying to find the angle in theta 2. Sorry, the angle in medium 2. So just use your calculator and you would find out that, sorry, theta 2 is, theta 2 is 16.36. Oh, ada kat sini dah. Okay, so this is your answer. One thing to take note is that you have to know this. N is equal to 1 for air. It's not going to be given. You have to remember that it is the same. It is approximated to be equal to the index of refraction of a vacuum, which is equal to 1. Okay, so water has an index of refraction of 1.33. So this is N 1.333. What is the speed of light through it? So we are going to assume here ada boundary lah, and the boundary is between air and water. It did not specifically mention this, but it's asking us what will happen if it goes through water. So it has to come from somewhere. So first draw your normal. Tapi dalam soalan ni dia tak minta pun, tapi tak apa, kita tulis je. So this is your angle of incident and you would be having some refraction and the angle would be towards the normal because water is denser than air. And if it is denser, then we know that water will have a greater index of refraction than air. So N2 will be greater than N1, but V2 will be less than V1. Sebab dia slow. Kita balik kan? Remember our ratio. V1 over V2, lambda 1 over lambda 2, N2 over N1. Dia terbalik. Kat sini pun terbalik. Okay. Speed of light. So how do we do this one? So we know that N is equal to C over V. Can we use this information? So N is 1.333. Speed of light is 3 times 10 to the 8 meter per second over V, which is speed of light in water. So just use your calculator. You will find out that V is equal to 2.25 times 10 to the 8 meter per second. Totally irrelevant, right? But saya nak tunjuk juga. So this is your answer. Benda ni bukan answer. Ni saya just nak cerita. Okay. Next one. A monochromatic light source What does that mean? A mono means satu, one wavelength light. Monochromatic light means this light only has one wavelength. Okay, and the wavelength is 490 nanometer. Okay, when passing through a liquid, okay, this is in air, bermula dia dekat air. So kita lukislah air passing through a liquid. We don't know what this liquid is. The wavelength reduces to 429. So here, the lambda was 490. And when it went into this medium, the lambda became 429 nanometer. It reduced. What is the liquid's index of refraction? So here, easy peasy, we just use the ratio. Kalau ingat lah, kalau tak ingat, susah juga. So N2 over N1, V1 over V2, lambda 1 over lambda 2. So again, these guys match. This is the odd one. Kena ingat jangan tersilap. Okay, so we have lambda and we also have refraction of, we will know that the N of air is equal to 1, right? Okay, so let's call this as N1 and this guy as N2. So N1 is 1, kita nak cari N2, N1 is 1, lambda 1 is the lambda in air, so this is 490 nanometer, and lambda 2 is over here, 429 nanometer. This guy cancels out with nanometer. I can just calculate terus. 490 divided by 429 will give me 1.1. What is into 1.14. And what is the unit for index of refraction? Anyone? Anyone wants to guess? Because I forgot to mention. What's the unit here? It's unitless, no units, it's just number. Okay, again, we have our ratio N2, N1, V1, V2, lambda 1, lambda 2. This guy is in nanometer, typically SI unit meter, tapi selalunya dia akan bagi dalam nanometer. Nano is times 10 to the minus 9. Kan? Okay, so this is also in nanometer selalunya. Kalau tak sama, if they give you 1 nanometer and the other as micrometer, please expand it. So this guy becomes, kalau ni nanometer and this guy is micrometer, this will become times 10 to the minus 6. This becomes times 10 to the minus 9 meter. Kena expand lah kalau tak sama. Kalau dua-dua nanometer, then you can cancel them out. So senang lah. So V1, your unit is macam biasa, velocity, meter per second, cancel out. This guy, no units. Dia seorang je yang tak ada unit. Again, the odd one. Okay, next one. A monochromatic beam of light in air has a wavelength of 589 nanometer in air. Okay, dua-dua kali. Has a wavelength. Okay, so lambda 1 is 589 nanometer. N1 in air is 1. Passes through glass, N2 is 1.52. And then through carbon disulfide, oh, we have 3. N is equal to, and 3 is equal to 1.63. What is the wavelength in carbon disulfide? Have I done this one? I don't remember. Okay. Okay, so there's two ways to do this actually. Either you can, 2, and then this is lambda 3. So we know that N and lambda is connected by the ratio, right? So N2 over N1. At this point, dah macam bosan dah tengok ratio ni. So V1 over V2, lambda 1 over lambda 2. But we don't care about V. We want to know about lambda. So let's use that. So V1 over V2. Let's try to find out what is the wavelength in lambda 2 first. So N2 is 1.52, N1 is 1, V1 is, why am I look to V1? Lambda. Lambda 1 is 589 nanometer. 589, and also this is what we're trying to find. So lambda 2 will become 1.52 divided by 589. Silap, 589 divided by 1.52. So this becomes 387.5 nanometer. This is not the answer because kita tak tahu lagi apa wavelength dalam ni. So again, next one, N3 over N2, lambda 2 over lambda 3. It has to be terbalik. Remember that. Okay, so N3 is equal to 1.63, N2 is 1.52, and lambda 2 is, this is what we found over here, 0.5 nanometer, and lambda 3 is what we're trying to find. So lambda 3 is going to be equal to 387.5 divided by 1.63 times with 1.52. So you would get 361.35 nanometer. Unit wajib. Wavelength always has meter somewhere. Okay, so this is your first approach. You can do it like this, or you can go for a shortcut whereby you equate N1 over N3 over, N1 over N3 is equal to lambda 3 over lambda 1. Remember, it's a ratio. You can just go straight forward to the ratio. So if N1 is equal to 1 and N3 is 1.63, lambda 3 is, lambda 1 is 589, right? So here I would find out that lambda 3 is equal to 589 divided by 1.63, which is 361.35 sama nanometer. So again, why does this work? Because it's a ratio. It is a ratio. So tak kisah ratio apa dengan apa, asalkan it matches. So I can say N1 over N5. Tapi ratio ni dia kena match dengan lambda 5 over lambda 1. It doesn't care what you're talking about as long as it matches. I mean, like ada wavelength yang corresponding to that ratio lah. Okay, so you can go with this long one, or you can just straight away go for N1 over N3, lambda 3 over lambda 1. Dua-dua boleh, dua-dua tak salah. Jalan kira jawapan, jalan kira punya markah pun sama. Tak ada penalty kat mana-mana kalau pakai shortcut. Okay, so we talked about refraction and we used the Snells Law to find out what was the angle. And we talked about index of refraction. Let me do a recap, small recap. We talked about N. N is equal to C over V. N is dependent on the speed of light. If you are traveling faster, you would have smaller N. If you are traveling slower, you would have a bigger N. Slower, bigger N. So this is typical for glass. This is typical for air. And we also talked about where air index of refraction is always going to be equal to 1 for our approximation. This is true for our exam and syllabus as well. And then we also talked about the ratio, which was N2 over N1, V1, V2, lambda 1 over lambda 2. And we also talked about Snell's Law. Macam tu je dia, Snell's Law. Huruf besar, ni nama orang. Kata nama khas. Snell's Law. Okay, so S pada N1 sin theta 1 equals to N2 sine theta 2. Okay, so this is going to be your incident medium, and this is going to be the refracted light over here. So N2 will be referring to the medium where the light is being refracted. Theta 2 will be the angle of refraction. N1 is the medium in which the light is incident ataupun dia start masuk. And then theta 1 is the angle with respect to the normal in the medium, in the incident medium. So how do we draw the boundary? Just draw a straight line. The normal will always be perpendicular to the boundary, and you have rays of light. You can either move towards the normal or away from the normal, and the angle is labeled with respect to the normal. Okay, so if this is the angle, that is your angle. Okay, so that is it. Next, moving on to the total internal reflection. Give me like 4 more minutes. Saya nak catch up. Saya nak cuba as much as possible. So TIR, total internal reflection. What was that? Okay, so we call it as TIR. So total internal reflection. I told you earlier, we looked at the glass yang warna merah tu kan, laser warna merah, glass warna transparent. So in this glass, we saw that the light was reflected balik dalam glass tu. And this is called TIR ataupun total internal reflection. So there are certain conditions that have to be met for total internal reflection to happen. So when light moves from a medium of high index of refraction to a lower index of refraction. So as you can see over here, this is glass and this is air. So dia kena N, of course, N of glass is going to be greater than N of air. So condition untuk TIR to happen is incident light kena berada dalam N yang besar. So we have this situation over here. Let's say this is water and this is air. Water punya N is going to be greater than N of air, right? So N water is going to be greater than N air, and W greater than NA. So this is the condition. So here we have angle theta incident, and mula-mula dia normal je, dia refracted macam biasa. And then as I increase the incident angle, saya besarkan angle dia, I can see that the ray of light is refracted away from the normal. Lagi besar angle of refraction dia. So lagi besar incident, lagi besar refraction. And then lagi besar incident wave saya, lagi besar angle of my incident wave ataupun incident light, the more dia akan travel away from the normal. At one point, dia akan travel betul-betul dekat boundary. Okay, again, mula ada incident light, they travel away from the normal sebab N1 lagi besar dari N2. So kita kat dalam ni speed dia laju kan. So dia akan away. And then as I increase the angle, yang ni akan move further away. And as I increase the angle further, dia akan reach a point where the refracted angle travels at the boundary. Dekat boundary. And this angle is called the critical angle. Refracted light will be 90 degrees to the normal. Buruk intuisan saya hari ni. So the reflected light is 90 degrees with respect to the normal. So angle dia sekarang bukan 30, bukan 50, is 90. Tadi macam 50, 30 kan. So now it's 90 degrees with respect to the normal, and the incident angle is called critical angle. And when your angle is greater than your critical angle, let's say saya besarkan lagi angle ni to become greater than the critical angle. So now instead of refracting, it will be reflected. This is total internal reflection. It happens when you shine light at an angle greater than the critical angle. Okay? So that is it for today. Kita akan sambung next class. Thank you everyone and have a great rest of the day. Bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you, Doctor.
Bye. Yes, Aizat, ada soalan ke?